We're going to go back as we go through this section. We'll go back and pull from a lot of things like your must-know functions and your analysis that we did. I know that excites y'all so much. So we're going to start with power functions, and we've done power functions. You just haven't known that they were power functions. So we're going to define them, and we're going to talk about them a little bit and what they do. So a power function is any function that we can write like this: k times x to the a. Okay. These are should be really familiar to you, and we'll talk about some ones that we've already done. K here is a constant, and it cannot be 0. We'll put non-zero. What do we call A? Not an exponent, but there's something else we can call it. A power. You're exactly right. Power. A is also non-zero. Constant. Come on. Another word we often use for the K in the front is called the constant of variation. I'm going to put AKA. Y'all know what that means? Okay. Good job. Constant of variation. And we often say, when it's written this way, okay, f of x varies as the eighth, not eighth, but eighth. Oh, y'all are rough this morning, rough crowd. Eighth power of x. Like the letter A. Or sometimes we say, and I'm writing these out, and there's a little blurb in your book that defines all these, but I'm writing them out because as you come across problems, it will say write a power function where f of x varies as the third power of x, or something of the sort. And so you'll need to understand what that means. It can also be that f of x is proportional to the eighth power of x. It's just that's what they're saying. If A is 7, then it would be the 7th power. If A is 12, then it would be the 12th power. It's just, we're just saying whatever that variable happens to be. Let me tell you some very common power functions that we use. Now remember, the K has to be non-zero and a constant. I'm going to buy a new pen one day, I promise. All right, so some common ones that you may not have realized were power functions, but they actually are. The area of a circle. What's the area of a circle?
Radius.
Pi r squared.
Thank you, pi r squared. Is that a power function? Yes.
Absolutely.
It absolutely is. What's the power? What is the constant?
Pi.
Yes, you didn't even let me finish. The constant of variation here is pi. And pi is a constant. Pi is a constant number. It's always the same thing, right? Can you think of another one? Can you think of one you've used before? Maybe not.
What is it, for a triangle?
Well, that's more than one variable in it. How about circumference?
Yeah, circumference is 2
To what?
pi r squared.
The r's not squared.
2 pi r.
What's the power?
Oh,
Mm. 1.
1.
What's the constant of variation?
2.
I'm fixing to make it a little bit harder for you. Come on. Ah. Constant of variation is. What'd you say it was? You said 2. It's not just 2. 2 pi. 2 pi together is a constant. 2 times pi is a constant. You might not be familiar with this one, but it doesn't mean you can't analyze it a little bit. Is that a power function?
No. Yes. No.
Yes? No? I don't know. Is it?
No. It's not.
I do know, but I'm trying to get you to think through it and reason through it. Justify.
Because for it to be that, it has to be multiplied. That's the pi.
Could you change that to a multiply problem?
Yes.
How?
By flipping it.
Flipping what?
The thing right there.
Rewrite this. F equals K times what?
K times D squared.
What happens if you flip this up to the top?
It turns into.
Good job, Jackson. Is it a power function then? Yes. It is a non-zero constant. What's the power? -2. What's the constant of variation? That number in front, right? That, by the way, is the force of gravity. Uno mas.
So how did you get?
Hold up, what happened?
Hold on, it takes a minute to think here.
How did you get K? Like if you're dividing, you always put it,
Yeah, yeah. That's the way it always works.
and whichever number is first, you need whichever.
All right. Tell me this. I told you I gave you 2 quotations, right, that we could read a power function as. F of x varies directly as the 8th power of x, or is proportional to the 8th power of x. Give me this in those kind of words. The area of a circle varies what? Jackson, finish. Varies
as second.
No.
Eight.
Varies to.
Varies
as
as the square,
the square
power of
He said
pi.
that's the 2.
as the square
I didn't know how to say it.
of its radius. If you see that written, would you understand what that means? No?
Yeah. Draw.
That's the area of a circle.
Draw.
I just showed you. I'm just putting it in words is all I'm doing. I'm just putting it in
And
words.
it varies as
We have to put it in.
All right. No, you won't have to put it in words, but if I give you words, do you understand what it is it's saying? Yeah. So when we talk about power functions, I hope you noticed, is this recording? Oh, yeah. We had some that had positive exponents and some that had negative exponents, right? Any of them with positive powers are what we call direct variation. I hope you've heard direct variation before. Oh my goodness. It means that two values are related by a constant of variation. Okay, that's where that constant of variation comes from. When we talk about direct variation, that constant multiplies to what they're related to. If it is a negative power, negative powers deal with division, right? We saw that one that had it on the bottom. When we moved it up, it became negative. That's what we call inverse variation. All right, let's look at a power function. We're going to graph it, and we're going to talk about some things with it. Oh, no, don't start that. Power function or nah?
Or nah.
Or nah. Or nah.
I'm just saying
Or. Can you write this with an exponent, as an exponent? Now you got to go back to algebra 2. Can you?
Wait, what do you
Nah.
write algebra 2?
You have the exponent.
Can you write a radical as an exponent?
No, it's okay.
You sure?
Yeah.
I'm going to say yeah. Think back, and I know y'all got to this. We all got to this in algebra 2. If you have the square root of x, that's an imaginary 2 that sits outside because it's saying what number times itself twice gives you what's under the radical. I could rewrite this as x to the 1/2. Oh my goodness, y'all are looking at me like you have never in your life seen this before.
You'll write it 1/3.
If I had the 5th root of x to the 3rd power, I could rewrite that as x close 3/5. Okay, you remember it? Okay. So my question goes back to: can you change this to have an exponent?
No.
Sure.
Yeah, it's one of the.
So if it's written this way, is that a power function?
Yes.
Yes. Does it have a non-zero constant exponent? Does it have a constant of variation in the front?
Yes.
Sure. Just because it's 1 doesn't mean there's nothing there. So yes, this is a power function, right? Is it an inverse variation or a direct variation?
Correct.
Why? It's positive, so it's direct. Are y'all following my thought process here? What I'm doing?
Like your thought process
Okay.
right here, I'm walking right.
Okay. Long as you close, like I can reach out and touch you, right?
Probably not. I can reach out to you my algebra.
Okay. As long as we close. All right. What does this look like on a graph?
It looks like a little
It's a variety.
snake.
Like a snake.
Okay, so it's not a parabola. It's not a snake. Okay, so you're thinking a cubic.
Yeah.
Okay? Turn that on its side. Because this is the inverse of that. So if you come in here, let me turn my plot off, because you'll be sketching graphs of these. You can put this in here as x to the 1/3, or if you go in your calculator, if you go into math, you see number 4, there's a 3rd root button.
See it.
Yeah, I see it.
Okay? You can also choose that option. And then do X. So Jackson, you were really close in saying that it looked like the cubic. There you go. But it's a cubic on its side is what it is. It's the inverse. All right, so if I were to sketch a graph, it would look something like this. Yeah. It's probably fixing to cut off. Y'all are crazy. It's not even that cold in here. What's the domain?
Negative infinity and infinity.
Why?
Because it doesn't have to be a
But there's a radical there. Why is the domain still negative infinity to infinity? When it's an odd number radical, okay, the reason that even radicals are restricted is because you can't have a negative under there, right? But odd number radicals, who did that crap? You're touching it. Okay, so do y'all understand the difference and why it's not restricted and a square root is? Okay, what's the range? That's okay. Negative infinity, infinity. Is it continuous?
Yes.
Why?
Because it's
See, y'all talked all that trash about analyzing functions and y'all.
some dependent domain.
I bet you know more. Over what intervals is it increasing?
1/3.
When is the function increasing?
At 0, 1, -1.
You're all right, you
Zero,
know.
0.
1, 1, 2, 2.
It's 0, 1.
You technically
When is the function increasing?
1, 1.
-1.
It always increases. Do you see that? It increases from negative infinity to infinity. It always increases. Keeps going. Keeps going up. Does it show any type of symmetry?
No. Yes.
Yes. I
Because
forgot how
it's
you.
odd.
It's odd. Why? How can you look at it until it's
If you
odd?
put a negative x, when you put a negative x, it's gonna
Look at you. If you put a negative x in there, it's going to completely be the total opposite.
It smells.
Does it have any maxes or mins?
No.
Yeah.
Well, it has
a related.
None. None. Because remember, if it's always increasing or always decreasing, it won't have any maxes or mins because those happen when it stops doing one and goes to the other. So it stops increasing and starts decreasing. That's the point where you have a max. Okay. All right. Last question on this one. What's the end behavior?
Okay, as x.
Uh-huh.
Goes infinity.
As x approaches infinity,
Y approaches infinity.
mm-hmm.
X approaches negative infinity. Y approaches infinity.
So tomorrow I'm going to teach you a new way to write end behavior with limits. We sure haven't gotten very far. We get at 950 or 955. I'm going to show you the limit. I'm going to show you limit notation real quick.
Wait, was that?
When we, that was like an eighth of it. We just didn't get very far. All right, in behavior. So what we've been doing is we've said as x approaches positive infinity, and we'll take the one that we did for that one. Y approaches positive infinity and as x approaches. So what we're going to do is as we get a little higher in math, we use what we call limit notation, which is exactly what kind of says the limit as x gets. So it's saying, is there something limiting the value? What's it getting close to? And so the way we write it is, and we'll put here limit notation. It's kind of like when I taught you interval notation and told you to use that, the negative infinity, and y'all hated it at first. You're probably going to hate this at first, but once you get used to it, it's not bad. So what we do is we say, and I'm going to just rewrite this in limit notation, the limit as x approaches positive infinity, it looks almost exactly the same, okay? But then what we do is we put the function right here. So we say the limit as x approaches positive infinity of the cubed root of x is, and then we tell what y does. Positive infinity. Okay? Look at the other end. The limit as x approaches negative infinity of the cubed root of x, what does it do? What does y do? negative infinity. Okay. Remember, if it approaches an asymptote, then it's going to equal that asymptote. Okay, if it approaches a number or anything like that. So this will be the new notation that we will use. This is not really hard to grasp or understand. Really, it's basically the exact same thing. We're just including the actual function with it. Makes it a little more mathematically correct. A little more, makes us look a little smarter. All right. Let me tell you what I want you to do, because we got through nothing that I wanted to get through today.
So, yeah, do know.
Unfortunately for y'all.